Welcome students. Today we will discuss the trend of ionization enthalpy or ionization energy when we move from beryllium to boron in the second period. Let us compare the ionization energies of boron and beryllium. Let us discuss about what do you mean by ionization energy. Ionization energy is the energy required to remove an electron from the outermost shell of an isolated gaseous neutral atom which is in its ground state. Here you should know the meaning of every term used here in the definition. The atom must be in isolated form. Isolated means it doesn't have any interaction with the nearby atoms and it is possible only in the gaseous state. Secondly, the atom must be neutral means there should not be any charge on that atom. And lastly, the atom must be in ground state, that is the minimum possible energy state for that atom. If you remove one electron from outermost shell of such atom, then the energy required for that purpose will be equal to the ionization energy of that atom. Now, what do you mean by the first ionization energy? It is defined as the energy required to remove first electron from the outermost shell of an isolated gaseous neutral atom which is in its ground state. On successive removal of second and third electron from the same atom, require second and third ionization energy respectively. Now we will compare the first ionization energy values of boron and beryllium. In general, when we move left to right in a period in the period table, the atomic size decreases and ionization enthalpy or ionization energy increases. It is because of increase in the effective nuclear charge. It means when we move from beryllium to boron in the second period, the atomic size decreases and the ionization enthalpy must increase. But actually it is not so. The ionization energy of boron atom is lesser than that of beryllium. Why it is so? Let us understand this on the basis of electronic configuration of boron and beryllium atoms. Atomic number of boron is 5. Therefore, its electronic configuration will be 1s2, 2s2, 2p1. You can check it. The last electron goes to 2p subshell in the boron atom. Whereas for the beryllium, atom number is 4. So, its electronic configuration will be 1s2, 2s2. You can see here that the last electron of the beryllium is filled into 2s subshell. It means in the boron, the outermost electron which is to be removed is in the 2p orbital, whereas in beryllium, the outermost electron is in the 2s orbital. Before going ahead, we have to understand one more term, that is penetration ability. Penetration ability of an electron in an atom means how close that electron can get to the nucleus in the atom. Lesser the distance of electron from the nucleus, more will be its penetration ability, and more the distance from the nucleus, lesser will be the penetration ability. To compare ionization energies of boron and beryllium, we have to use penetration ability concept. Now, what is the trend of penetration ability among the various orbitals in the atom? If you compare the penetration ability of s orbital, p orbital, d and f orbital, then you will find s orbitals have highest penetration ability, means they can go to the closest distance to the nucleus. Whereas p orbitals have lesser or lower penetration ability in comparison to the s orbital, means they stay farther from the nucleus in comparison to the s orbital. D and F orbitals have even lower penetration. It means D orbitals have lower penetration ability in comparison to P, and F orbitals have lower penetration ability in comparison to D orbitals. Now come back to the topic. As we have already discussed that the last electron in beryllium goes to 2s orbital, and the penetration ability of 2s orbital is highest among the orbitals of second shell. It means the electron of 2s will be close to nucleus and there will be high attraction from the side of nucleus on it. So, if you want to remove this electron, you have to give a very high amount of energy, and therefore the first ionization enthalpy of beryllium will be high exceptionally. There is a misconcept related to the ionization enthalpy of beryllium, that the high ionization enthalpy of beryllium is due to the removal of electron from the fulfilled s subshell configuration present in the valence shell, which is highly stable. It is totally wrong because S subshell has a single orbital, and therefore there will be only three states possible. When there is no electron, it will be empty. When there is one electron, it will be half filled. And when there are two electrons, it will be full filled. So there are only three states, and all the three states are stable. So how can we say that the electron, when released from such a configuration, will require a very high amount of energy? And therefore this concept is not applied here. This concept is valid for the D subshell, F subshell, and P subshell, where there are more than one orbital present in the subshell. In case of P subshell, there are three orbitals. So if there is zero electron present, so it will be empty. When there are three electrons, then it will be half filled. When there are six electrons, then it will be full filled. And if you say that there is one electron or two electron or four electron or five electron, then these states are totally different from empty, half filled, and full filled subshell configuration, and they will be lesser stable. So half filled and full filled subshell configuration concept is valid for P, D, and F subshells where there are more than one orbital. It cannot be applied on S subshell. So high energy enthalpy of beryllium cannot be explained on the basis of full-filled S subshell configuration. Now, if we talk about the boron atom, the last electron goes to 2p orbital. The penetration ability of 2p electrons will be lesser than 2s electrons. It means the electron of 2p orbital will be far from nucleus, and the hold of nucleus on this electron would be weaker, and therefore it will be easy to remove this electron, and therefore the first ionization enthalpy of boron is exceptionally lower, even though the atomic size of boron is smaller than beryllium. Now I hope that all of you have understood this concept clearly. If you like this video, kindly subscribe and press bell icon to receive notification for the new video as I make it for you. Thank you very much.